All right, everyone. So let's just recap where we are at here. Right now, at this stage of the course, we're on Chapter 15. Today is March 12th, 2021. So pretty much I think we're at the halfway point of the term. So I think there's another 6 to 7 weeks left of class. Everything should be downhill from here. So now's the time to really do what you need to do to get the grade you want. Like I told you guys before, now I'm recording. I submitted your midterm grade. It's not your final grade, and it's not the grade that will go into your final transcript. So there's opportunities to raise that grade. For one, there's quiz 2, quiz 3, quiz 4, lab reports, and then there's a lab notebook you'll turn in at the end of the semester. If you signed up for Clutch Prep, if you do everything, all their assignments, I'll also give you some points to your final grade. So there's a lot of opportunities to raise your grade. Right now, there's 3 students that have an A. Okay, A as in like 97%. Okay. There's one student with a 97.8% or something like that. Okay. So, but that's the midterm grade. That's not the final grade. Right, where we left off here is we're talking about acid-base chemistry. So some equations I'd like for you guys to know. One thing is I want you guys to know, well, let me tell you what you should know, okay? Let's make things as simple as I can possibly make it, okay? The first thing, things to know. The things I want you to know are the 6 strong acids. So can anyone list those 6 strong acids? Okay, we're 4 strong. If we had 2 more students, we'd have every individual can represent a strong acid. So one of them is HCl. Anybody have another one? Sulfuric acid, excellent, thank you. Hydrobromic acid, HBr. We have 3 more left. HI, hydroiodic acid. 1, 2, 3. Okay, 5 and 6. Nitric acid, excellent. Okay, thank you, Ariana. And one more. Okay, there's an acid called perchloric acid. We don't see that a lot. You haven't seen that maybe in your lab, but it is also a very strong acid. So these 6 I want you guys to recognize as strong acids. Okay, I'll call strong acids SA. So these will give 100% protons. So as an example, HCl will close to 100%. Nothing is 100% in science. So that's why I'm putting the arrow in the forward direction. Will 100%, quote unquote, go to H plus and the conjugate base Cl minus. Okay, like that we can go ahead and fill out the rest. 100% or close to 100%. So the Ka equilibrium constant, not even an equilibrium, because I noticed the way I draw the arrow, it's very, very, very large. Okay. So that's one thing that we need to know. I also mentioned to you some strong bases. Anything with an OH minus would represent a strong base. Okay, so here we're talking about, your sodium hydroxide, potassium hydroxide, lithium hydroxide. Anything with OH minus, these would represent what I'm going to call the strong base. And I'll label that with an SB. So these are what we'll call strong bases. Finally, there are weak bases. The classic example of a weak base is NH3. There's a lot more weak bases out there, but I just want you guys to, if you were to memorize anything, memorize that NH3 is an example of a weak base. Okay, NH3 is called ammonia. Right, so there's a lot more weak bases in nature. There's a lot more strong bases in nature. These are the 6 strong acids that I'll just want you to know for this class. Everything else is just a weak acid here. All right, so let's talk about weak acids. So this is the first thing that I want you guys to know. The second thing I want you guys to know is the weak acid, weak base equilibrium. All right, this is something I definitely would like for you guys to recognize. First, let's talk about weak acids. All right, HA plus H2O. It's weak, right? It's a weak acid. So instead of the arrow going one way, let's have the arrow going both directions. Acids do what acids do. Brunstad acids, they give away protons. Okay, they give away protons. And we will get H3O plus, aqueous. Notice this is all happening in the medium of water. This is all happening in the medium of water. So we give off an H plus, water becomes H3O plus, and HA becomes the conjugate base A minus. And let's, I know you'll have this for your next exam. I know you're not thinking about maybe perhaps test 3, but in test 3 you'll have to recognize, look, this is the acid, and the acid comes along and we have a conjugate base. This is the base, and it generates the conjugate acid. We have a back and forth arrow here, which means this is at an equilibrium, and there's a Ka associated with this equilibrium. Right, the Ka for this equilibrium is going to be products over reactants. Somebody did this on the, I think it was the quiz, not the exam, on the quiz. They put the liquid in the equilibrium constant. So that's still happening. Don't put solids or liquids in here. Okay, it's just products over reactants. They get raised to the 1 power because each of these has a coefficient of 1 attached to it. So an example of this would be acetic acid. Okay, this is kind of like your vinegar. Acetic acid will give that H plus. You'll have H3O plus aqueous plus the conjugate acid. Okay, that's Ka. As an example, okay, this is the example of acetic acid. All right, let's do the Kb for this. Okay, in the Kb, we'll start with acetate. So you have to know Ka. That's the one thing we need to know. We're talking about things to know here. And then you have to know the equation for Kb. Here, so recognize that this is the base. Okay, water is going to act as the acid and give away the H plus. Very fascinating how water can do both things. Here on the above equation, we're acting like a base, taking that proton from the acid. In the Kb, with the acetate ion, water is donating the proton. Right? Everyone see that? Water is truly a remarkable molecule. truly is. And so this H2O gives away that H plus. It becomes OH minus. And this acetate becomes acetic acid. This is your Kb. So you should know what the Ka looks like and what the Kb equation looks like. All right. So the Kb equation would be, sorry. The Kb equation would be OH minus times your acid. Here I'll call the acid HA divided by the base, conjugate base. Here I'll call the conjugate base A minus. So this is the generic formula for Ka, and this is the generic formula for Kb. Here we have a specific equation for Ka. Here we have a specific equation for Kb. All right, so you should know the Ka and Kb equations. Okay, that's one thing that you guys should know. So let's add these two together. Okay, I'm going to add Ka and Kb. So here's the acetate will cancel. Here acetic acid will cancel. We're left with one H2O plus another H2O gives us two H2O. And that's at an equilibrium with H3O and OH minus. Okay, this is something you need to know with the conjugate acid, conjugate base pair. When you add two reactions, you multiply the equilibrium constant. So the new equilibrium constant is Ka times Kb. We will designate that as Kw. So here's something that you guys should know. Kw, we looked this up in the textbook. Kw equals 1.00 times 10 to the minus 14 at 25 degrees C. Okay, remember, we quote an equilibrium constant at a specific temperature. The equilibrium constant for Kw is products over reactants. So again, these are things that you guys should know. All right, let's continue on with this. Everyone can let me move on here. I just want to show you guys something with this. Kw equals Ka times Kb. Okay. Taking the Ka for any weak acid, taking the Kb for any weak base. Okay, what's common between these two? Water. Okay. Water is common in the Ka reaction and the Kb reaction. Okay, make sure you know how to write a Ka reaction, know how to write a Kb reaction for the quiz or the next exam. Looking at this for a second with me. Kw is equal to Ka times Kb. Okay. I'm going to take the minus log of both sides of the equation. So here this becomes minus the log of kW equals minus the log of Ka times Kb. So there is a math rule. This is not something that I expect you guys to know. But for those of you that can get a little bit better appreciation, if you know this log rule, log A times B is equal to log of A plus log of B. Okay. Which means instead of AB, I'll do log of Ka times Kb. Okay, that's going to equal to the log of Ka plus the log of Kb. Okay. But remember, you see here I have a minus. Everyone see that minus? This is a log rule from trigonometry. But you see here I have a minus. So I'm going to have to distribute the minus. So when I distribute the minus, because it's a minus here, the minus distributes. So it's going to be minus log Ka plus a minus log Kb. So this is going to be minus log Ka times Kb equals a minus log Ka plus a minus log Kb. So we're not interested in, I'm not going to ask you any derivation questions, but I just distributed that log. I just distributed that minus sign. So minus log Kw is equal to minus log of Ka plus a minus log of Kb. Again, I just distributed that minus sign. Okay, minus log of Kw is something called pKw. Okay, remember that P stands for power. And it's minus the log of whatever. Okay? Minus the log of Ka is pKa plus minus the log of Kb is pKb. So here we have another equation. That's pretty good. pKw equals pKa plus pKb. Okay, we already know what Kw is. Okay, at 25 degrees, Kw is 1.00 times 10 to the minus 14. Okay. So we'll put that Kw value right here and take minus the log of 1 times 10 to the minus 14. Okay. Putting that Kw right here and minus the log of that. Minus the log of 1.0 times 10 to the minus 14 is 14. So 14 is equal to pKa plus pKb. So not something, you do not need to know the derivative, how we derive this equation, but this is the next big equation on our list here. Okay, in fact, we have three equations so far. Okay. This is from Monday's lecture. Okay, we had Kw equals H3O times OH minus. This is again from Monday. We have 14 equals pH plus POH. Again, this was from Monday. And now we have 14 is equal to pKa plus pKb. So we can use all of these equations to our benefit. So let's do a summarization. Summarizing our equations here. Okay. Summary 1 is pH plus POH is equal to 14. Okay, what is pH? Okay, that little P stands for power, and power is minus the log of whatever. So here it's going to be pH is minus the log of H plus. Okay, H plus, H3O plus, same thing in my book. POH is minus the log of OH minus. H plus times OH minus, the concentrations is equal to 1.00 times 10 to the minus 14. And a couple of more equations here. pKa is minus the log of Ka. pKb is minus the log of Kb. And then this equation here rounds everything up. pKa plus pKb is equal to 14. Right, here's our acid, here's our base, and the only tricky little twist here is that we have power minus the log. Okay, pH, power of the H plus, POH, power of the OH minus, pKa, power of your equilibrium constant Ka, pKb, power of your equilibrium constant Kb. So definitely we will see this in your homeworks. You will see this on tests, quizzes. You'll probably see this in your future chemistry classes or MCAT or whatever professional classes you're taking. Let's say we want to go back. Okay, let's say we want to get H plus out. So H plus is going to equal 10 to the power of the minus pH. Okay. That is on your calculator, the anti-log. You see that? Okay, don't use the log. Use the anti-log. Okay, the anti-log is this thing above the log. Okay, we will do some problems with numbers so you can see what I'm talking about. If you want to get the concentration of OH minus, if you have the POH, it's 10 to the power of the minus POH. Again, don't use the log when you're doing the math. You're going to use the anti-log. Okay, the number above the log. The number just above the log. Same thing here. Okay, let's say you're given a problem. They ask you to find Ka. You can find Ka is equal to 10 to the power of the minus pKa. And then finally Kb. Okay, this is going back and forth, Going back and forth between the two. Kb is 10 to the power of the minus pKb. Okay. So part of this class is knowing a little bit, not a lot. Okay, we let our calculator do this. Is knowing how to be comfortable with logs, and in this case, anti-logs. Okay, 10 to the power of minus pH, 10 to the power of minus POH, so on and so forth. All right, we will do some specific examples of this. Let's go back to our lecture notes now. Anybody still need this here? Keep it up. Okay, do not need to know any of this. Okay, if there's anything that you guys need to know, it's going to be this. This will definitely help you guys navigate this material very easily. Okay. We probably know pH. There's a lot of biology majors here. And, we live in a pH world. Everyone knows about pH. Nobody talks about POH. I always wonder, hey, what's your pH of the blood? Nobody says, your doctor never says, sir, the POH of your blood is too low. It's abnormal. They say your pH is too abnormal, right? But they could really also just say POH, right? Because pH plus POH is equal to 14. I just reminded myself, pH is unitless. And also POH obviously is also unitless. All these equilibrium constants are unitless. POH, pKa, pKb, We just don't put units in them, okay? This is one thing I noticed when I graded the quizzes and the tests. People were putting wrong units. In the case of pH, POH, you don't have to put units. Okay, don't put units. In fact, log, I don't know how pure of a math background you guys want, but you're technically, I don't know, whoever created logs. It's very explicit that units do not go into the log. Units do not go into the log. So pH being the minus log of something, you don't put units inside the log. Okay. Bottom line, these guys have no units. All right. Let's go to our lecture notes here a little bit, and we'll wind up the class, and for some of you, the weekend. We'll start the weekend. Wait, I'm going to start on page 3 of our lecture notes for those that are following along. If not, this lecture is already recorded for you guys. So what I have here is a table with some acids, okay? We have HCl, which is a strong acid. H2SO4, which is one of our 6 strong acids. Here's HSO4. There should be a minus sign there. Here's HNO3, which is a strong acid. Okay. Here's phosphoric acid. And what we see here is all their different Ka equations. Right? Even have water here. Okay. Here's our classic example of a weak acid. That's acetic acid. So classic weak acid example. And these are all the different equations. So as a summary, okay, water's in it. Okay, water's taking that proton. Okay. And all of these reactions, the acid gives off H+. All of these reactions are at an equilibrium. All of these reactions are at an equilibrium, but, you know, for your strong acids, it's overwhelmingly to the product side because they're strong acids. Okay. And all of them give rise to H+ in the form of H3O+ and the conjugate base. All right, so the reason why I drew that arrow so single-handedly pointing towards the product side is because check out the value of the equilibrium constant. Excuse me, check out the value of the equilibrium constant, 1.3 times 10 to the 6th. Okay, I told you Ka is unitless. What if I gave you the units of dollars? Here, Joshua, I'm giving you 1.3 times 10 to the $6. That's 1.3 and put 6 zeros by it. Is that a lot? Okay, you won't be here probably, drive a Ferrari or something. That's a lot. Okay, that's a huge number. Okay, remove the dollars, and just as a number in it of itself, it's a large number. So such a large number means the reaction is essentially, and it's like that for all the strong acids, the reaction is essentially 100% going in the product side. That's why I draw this in this way. And you can do that for all your strong acids that are part of our magic 6, the 6 strong acids. All right, so Ka, and I looked these up in a book, in a table. We can do the pKa minus the log of Ka. Okay, minus the log of Ka, power of Ka. And this is our pKa, remember? All right, if I do the minus the log of 1.3 times 10 to the 6th on my calculator, I get minus 6.20. Okay, a very, very small number for a very, very large Ka. So looking at this, what do you guys think? The larger the Ka, okay, the stronger the acid, right? Sorry. Larger the Ka, stronger the acid, right? 1.3 times 10 to the 6, such a huge number. Okay, stronger the acid. What about the pKa? Higher or lower? Very good, okay. The lower the pKa, the stronger the acid, okay. What I want to convince you guys is that your pKa is large. Imagine, Josh, you have 1.3 times 10 to the $6. It's a lot, okay? But the pKa, it's just the way the log math works. It's just the way the log math works. The lower the pKa, the stronger the acids. Okay, I want you guys to just realize that these two basically are the same. It's a measure. Okay, it's a measure of how well something is as an acid. So the larger the Ka, better the acid. Lower the pKa, the better the acid. It's just how the log math works. Okay. The reason why we did minus the log, you see 1.3 times 10 to the 6th is kind of a bear to write and a kind of a little bit annoying. See, scientists are all lazy. So if we can find a way to just make that number a little bit easy on the to write or easy on the to say, it's much easier just to say minus 6.2. Okay, it's much easier to say minus 2.1 instead of 7.1 times 10 to the minus 3. Getting rid of the messy exponents is what minus log does, which is what power is, minus the log of something. All right, so this is one thing I want you guys to recognize. Okay, this can be a little bit tricky on any exam, but Ka, the larger the value, stronger the acid. Lower the pKa, stronger the acid. Okay, these two mean the same thing, and remember pKa is minus the log of Ka. Same thing goes with Kb. All right. Higher the Kb, the stronger the acid, stronger the base, I'm sorry. And that just means your pKb. Again, because of the mathematics behind minus log, we have a stronger base. So that's one of the important things to take home from today's lecture. This Ka, pKa, the Kb, pKb relationship. One goes up, the other goes down. Both mean strong. Both mean strong. So on the exam, you'll rank acids based on their strength. Okay. So which do you think is the strongest acid here? The strongest acid here is the one with the strongest, highest Ka. Which do you think is the weakest acid? Out of this list, which is the weakest acid? Minus 13. That's pretty weak. Okay, that's a very weak acid. What is that? Minus 13. Such a small number. Okay, what is that called? I think monohydrogen phosphate. But water here, 10 to the minus 14, looks to be a very weak acid. It also is a weak base. Okay, so look at the number. Look at the number. All right. Smaller the number. Okay. Higher the pKa. Okay. Look at this number, 10 to the minus 10. Do you think NH4 plus is a good source of protons? Okay. Its equilibrium constant is 5.8 times 10 to the minus 10. Is that a large number or a small number? It's a very, very small number, right? 10 to the minus 10. So take the pKa of that, you get 9.24. Okay. Smaller the number, higher the pKa, weaker the base. Okay, so that's the relationship we guys should know. It's right here. Let me go ahead and complete this. let me just complete this here. The lower the Ka, that means the higher the pKa, and that means a weaker acid. Remember, we want to rank these. And then finally for Kb, the lower the Kb means the higher the pKb. Okay, it's just the formula. That means we have a weaker base. Okay, and all of that is summarized right here. Okay. All of this is summarized right here. Right here we have tables of Kb. Okay. Kb. So what is Kb? Okay, we start with the conjugate base. Okay, one thing that's very clear is that water is added again. Okay. Here, water is giving the proton. Okay, the opposite of our previous table. Here, water is giving the proton, and like all these equations, we get the conjugate acid and we get the conjugate base. Okay, notice what we produce in all of our Kb reactions. Okay, OH minus. So all right. So So out of these Kb's, which do you think is the strongest base? It's 10 to the minus 21. That's a small number. 10 to the minus 17. That's pretty small. Okay, minus 17. 10 to the minus 16, 10 to the minus 16, 10 to the minus 12. These are pretty small numbers for Kb. So we're really talking about weak bases here. Something like this, 0.0238, 2.38 times 10 to the minus 2. That seems to be a pretty strong base. That's phosphate. Okay. Phosphate. So again, the same ranking occurs. The higher the Kb, which implies lower pKb minus the log of Kb. That means the stronger base. By the way, take a look at this reaction with me. Let me see if I can highlight it. I'll highlight it in orange. Okay, let's just look at this reaction together with me. Okay, Cl minus plus H2O goes to HCl plus OH minus. What is our conjugate acid here? Is it not HCl? Right? So our conjugate acid is HCl. What do we know about HCl? It's a strong acid. Okay, so it's a strong acid. What do we know about Cl minus? Okay, it's very weak. Okay, it's a very weak base. So do you think Cl minus is a good source of OH minus? All right, let me repeat it again. Do you think Cl minus chloride ion is a very good source of OH minus? Okay, no, right? 7.7 times 10 to the minus 21. Do you have that in your account? 7.7 times 10 to the minus 21, minus 21. So now Cl minus is a poor source of OH minus, okay? But HCl is a fabulous source of H plus. Okay, let's go back to our HCl reaction. Okay, look at this reaction with me. Do you think that's a good acid? have 1.3 times 10 to the 6 in your bank account? That's huge. Okay, so yes, HCl is a part of our 6 that I told you to memorize, part of our 6 strong acids. So it's a good source of H3O+. But Cl minus, the conjugate base is a bad source of OH minus. Okay. The conjugate base is a bad source of OH minus. 7.7 times 10 to the minus 21 for this reaction. Bad source of OH minus. HCl giving rise to H plus. A fabulous source of H plus is this reaction. Once again, 1.3 times 10 to the 6th. Okay. So just table, these notes just tell you a little bit about water. I'm not really going to go into this, but I did an ice table for water, and if you do the ice table for water, and we will do lots of ice tables in this chapter, you will see that the concentration of H plus and the concentration of OH minus comes out to 1.00 times 10 to the minus 7. Okay, so remember our equilibrium for this. Is equal to Kw. Okay, that's our Kw value at 25 degrees. Again, we looked this up. And if you go ahead and do the ice table, which I've done here, you'll find that X, which is the H plus concentration, and X, which is the OH minus concentration. You'll find that X, which is the H plus concentration, and OH minus X is the OH minus concentration. That X is going to equal to 1.00 times 10 to the minus 7 molar. Okay. At equilibrium. So if you think about this, if you have the purest of the pure water, imagine the most purest water that you can ever find, the purest, most purest water you can ever find, it has protons in it. At what concentration? 1.00 times 10 to the minus 7. It also has OH minus in it. The purest, I'm talking about the purest water ever. It also has OH minus in it, in that water. At what concentration? 1.00 times 10 to the minus 7. So out of every, I had this statistic and I forgot the exact number, so you'll have to forgive me. I think for every 100 billion water molecules, I don't know the exact number, again, I'm sorry, for every 100 billion water molecules, you get one H3O, H plus. And for every 100 billion or so water molecules, you'll get one of those will be OH minus. Okay, so that's the extent that water goes in this direction and giving you H plus and OH minus. Let's see if we can finish this last page, and then we'll resume next week doing some math problems. I just want to tell you guys about the pH scale. Okay, so all right. So this is what we derived coming from this equation. products over reactants. Here's the KW that we looked up at a specific temperature. And using the ice table, we found that X is equal to 1.00 times 10 to the minus 7. So we will do the pH of that, which is the minus log of the H3O plus concentration, which is minus the log of 1.00 times 10 to the minus 7, which is equal to 7. Okay. Okay, so this value we got from the ice table in the previous page. We didn't do the ice table. It's in our previous page notes. Doing the ice table for this reaction. Getting X, which equals H3O plus, we get it at 1.00 times 10 to the minus 7. Taking the pH of that minus log of that concentration, we get 7. Okay, so POH will also equal 7. Okay, because pH plus POH is equal to 14. So in that situation, we have what's called a neutral solution. Okay, remember this is a scale. Okay, if you are below 7, we call that an acidic solution. Okay. So neutral solution is when your pH is equal to 7. By the way, it also means when your POH is equal to 7. Okay, so nobody tells, people kind of discard that or disregard that. Acidic solution is when your pH is less than 7. By the way, it also means when your POH is greater than 7. Remember, those two must equal to 14. And then I'll end the lecture with this. When you have a basic solution, your pH is greater than 7. pH scale 8, 9, pH 9, pH 10, pH 11. And that means your POH must be less than 7 for a basic solution. Okay. I think it's 1:50 now, so there's only 4 of us here. If you want to do the lab, I can help you. We can finish it off so you can be done with it. If not, you can do it next week. But I'll be here and I can be your partner. All right, so this is the pH scale. This is where we'll leave off and continue our talk on Monday. All of this stuff is kind of a review of the equations that I kind of went over at the beginning of the class. All right, I'll see you guys.
Doctor, they're saying for the base, the pH is greater than 7, and the POH is less than 7?
For basic, yeah. Yeah, basic. For now, just know if your pH is greater than 7, it's basic. Which means the solution has more OH. The solution has more OH minus than H plus.
But for the acid, it's saying right there you got rid of the POH is still less than 7. So.
For an acidic solution, the pH should be less than 7.
But yeah, we're talking for the POH.
Oh yeah. The POH should be less. Yeah.
Sorry, I was just confused for.
Yeah, they have to equal to 14. Well, they have to equal to 14. pH plus POH has to equal to 14. So.
Okay.
Yeah. So if your acidic solution pH is definitely below 7. That I know.
Yeah,
Your stomach is pH 2, right, to digest all the foods. So if that's the case, your POH, remember pH plus POH must equal 14, then your POH must be greater than 7. So, yeah, you're right.
I don't think we ever use any labs with POH, always pH.
Correct, yeah. But you can easily get to POH because, again, pH plus POH is equal to 14.